Okay, today we are looking at notes number 28, continuing in chapter 5. I think we're in section 5.6. After today, we're going to kind of veer out of the book and go off in our own direction. And today's topic is called the rational root theorem. So I think yesterday we had a couple of theorems, and today we have a theorem. And you know, we're not proving any of them. So I know that's disappointing. I think we should have a moment of silence for the fact that we're not proving these theorems. Especially those of you who were in honors geometry last year, I suspect you might be a little let down, so I apologize. Some theorems in math are proven using techniques that go beyond where we are in our level, and also sometimes we just have to let go because of time, especially this year. Okay, so what I am going to do is justify the theorem with these three examples. So we're going to start with a couple of quadratic functions. We're going to find the roots, and then we're also going to do a quartic function, find the roots, and look for a pattern. So let's look at number 1. We have g of x, and if we're going to find the roots, then we need to find the points where the y-coordinate is 0. So let's put 0 in for g of x. This is factorable. I'm just going to speed things up for us a little bit. I've already factored it. We get 3x plus 5 times 2x minus 7, and then set each factor equal to 0. And solve each one, and we end up with x equals negative 5/3 or positive 7/2. So those are the roots. So let's move on to number 2. Very similar process. We're going to put 0 in for f of x, and then we're going to factor it. This one factors as well. I purposefully made these examples factorable because we're looking for a pattern to find rational roots. And if it's factorable, it has rational roots. This factors into 4x plus 5 times 3x minus 1. So we set each of those equal to 0 and solve, and we get x equals negative 5/4 or 1/3. So those are the roots. Notice that both of these problems have rational roots. That's intentional. And then for problem number 3, I've already factored this, so let's set it equal to 0. And I've factored it into x minus 1 times x plus 1 times x minus 2 times x plus 3. How did I do that? I used synthetic division, and I tried different things until I found some that worked. So set each of those equal to 0. And solve each one. And we have our roots, x equals 1, x equals negative 1, x equals 2, and x equals negative 3. And these are all rational. Remember, rational numbers are numbers that you can write as a ratio of an integer over an integer. And so these could be written as whatever number you see over 1. Okay, what I want you to notice is what's going on here with the numerators and denominators. So let's take a look at number 1. The numerators 5 and 7, or we could say negative 5 and 7 if we want, those are factors of 35. In number 2, the numerators 5 and 1, those are factors of 5. And in number 3, the numerators 1, negative 1, 2, and negative 3 are all factors of 6. Now let's look at denominators. Going back to number 1, 3 and 2 are factors of 6. 4 and 3 are factors of 12. And then these denominators, 1 is a factor of 1. Okay, so it's looking like the numerators are factors of the constant, and the denominators are factors of the leading coefficient. Now we can explore this a little bit more. So let's say that I had some polynomial p of x, and it factored into these factors. ax plus b times cx plus d times ex plus f. Would you agree that if you were going to multiply those three factors together, that your first term would be a c e x cubed from multiplying ax, cx, ex together. And then you would have a bunch of other terms, and then your last term, your constant, would be b, d, f, and that's from multiplying b, d, and f together. So it seems like it's logical in general that the factors have as their constant factors of the constant, and that the leading coefficients have as their are factors of the leading coefficient, is what I'm trying to say. So that leads us to the rational root theorem, could also be called the rational zero theorem. So if f of x is a polynomial function with integer coefficients, that's important. It's also important that it has a constant in it. Then every rational root of f has this form. Remember, these are just the rational roots. The rational root p over q, where p is a factor of a naught, the constant, and q is a factor of a sub n, the leading coefficient. Now, don't forget that there could be irrational roots to a polynomial and non-real roots to a polynomial. So this theorem only refers to the rational roots, the ones that you can write as fractions. How would you get irrational roots? If you think about what you do with a quadratic, it's when you use the quadratic formula that you find your irrational roots, like 1 plus or minus square root 3, or even when you use the quadratic formula that you find your non-real roots, like 2/3 plus or minus square root negative 5 over 3, or something like that. So you're going to have, if you have irrational roots and if you have non-real roots, you're going to have two of them because of the plus or minus. They will be conjugates. They come in pairs. So irrational roots come in pairs, conjugate pairs. Non-real roots come in pairs, conjugate pairs. One with a plus, one with a minus, otherwise they are the same. Okay, so we're going to add this piece of information about roots to our toolbox of all the other things we know about polynomials at this point, and it's going to help us get to the point where we can do something with bigger, more complicated ones. So here's where we're going with the rational root theorem. Take a polynomial function like this one in number 4, and we're going to make what I call the APRR list. That means all possible rational roots, APRR. What we're going to do is narrow it down from infinitely many rational numbers out there in the world to just a finite list of those that could possibly be the roots of this. This is our candidate pool. Okay, these are all the contenders. So here's how we make the APRR list. Remember that the numerators have to be factors of the constant, and the constant is 10. So that would be plus or minus 1, 2, and 10. So there's 6 different numbers the numerators could be. Plus or minus 1, plus or minus 2, plus or minus 5. Oops, I missed one. 10. I said 10, I didn't say 5 a minute ago. So there's 8 different numbers the numerators could be, plus or minus 1, 2, 5, and 10. I just write the plus or minus once because it's too tedious to write it each and every time. Now the denominators, according to the rational root theorem, would be factors of the leading coefficient, so that would be plus or minus 1, 2, 3, and 6. Got it that time. So then the APRR list is the list of all the possible combinations of those numerators over those denominators. So what I'm going to do first is put all the numerators over 1, so plus or minus 1, 2, 5, and 10. And then all the numerators over 2, so plus or minus 1/2, 2 halves, which is actually just 1, and it's already in the list, 5 halves, and 10 halves, which is actually just 5, and it's already in the list. And then let's put all the numerators over 3, so we have 1/3, 2/3, 5/3, and 10/3, and then let's put all the numerators over 6. So we have 1/6, we have 2/6, which is just 1/3, and we already have that. We have 5/6, and we have 10/6, which is just 5/3, and we already have that. So here's what we're saying. In this list, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, times 2 for plus or minus 24. Only 24 possible rational roots narrowed down from a list of infinitely many. So that is good progress. Now, part B, find the roots. Okay, let's actually do some synthetic division, trying some of these numbers to see what the roots are. Keep in mind that as long as we can find one of them, we'll then be able to whittle it down to a quadratic and easily find the other two. So let me try x equals 1. Using synthetic division. Now, you might try something else first. I might try something else first. I might take several tries to find something. You might take several tries to find something. You never know. Bring down the first number. Multiply by the number in the box, write it down and add. Multiply by the number in the box, write it down and add. Multiply it by the number in the box, write it down and add. Okay, this is good. Lucky me, I found one on the first try because I got a remainder of 0. And these numbers that we see here represent the remaining quadratic, which would be 6x squared minus 4x minus 10. Keep in mind that the roots of that quadratic might be rational, they might be irrational, they might be non-real. We're going to find out. We're going to set it equal to 0. Let's divide it by 2. Make things easier on ourselves. I'm going to try factoring. Might as well try. There aren't that many options, so we can figure out pretty quickly if it's going to work or not. Looks like it is this time. So, set each of those equal to 0 and solve, and we have 2 more rational roots. We have 5/3. Notice that 5/3 is in our list of all possible rational roots, and we have -1. Notice that -1 is in our list of all possible rational roots as well. So the roots are x equals 1, x equals -1, x equals 5/3. Okay, let's try another problem. Same idea. We're going to make the APRR list and find the roots, but I'm going to show you something called the chart method. And you might think that for this problem, the chart method is unnecessary, but as the problems get bigger and more complicated, the chart method is going to be extremely helpful in figuring out your roots and looking for other things that you're going to need to know. So you're going to have to trust me today. If I show you the chart method and you think it looks like too much, just believe me, as we move on in the next few days, it's going to be really important. So first of all, let's do the APRR list. So our numerators would be factors of 6. So we have plus or minus 1, 2, 3, and 6. And our denominators would be factors of 6. So we have plus or minus 1, 2, 3, and 6. And then that means that our APRR list, which consists of all the combinations of those numerators over those denominators, would be plus or minus 1, 2, 3, 6, and then over 2. 1/2, 2/2, 3/2, 6/2. I'm not writing the ones that are duplicates of numbers we already have. And then everything over 3. 1/3, 2/3, 3/3, 6/3, and then everything over 6. 1/6, 2/6, 3/6, 6/6. Okay, so that's it. So now, let me show you what I mean by the chart method. I'm going to go off and show you using a different example. So here I have a different function, and if I was checking to see if x minus 0 was a factor, then I would put 0 in the box and do synthetic division and look at my remainder. And then if I wanted to check to see if x minus 1 was a factor, I would put 1 in the box, do synthetic division, and look at my remainder, etc. X minus 2, here's my remainder. X plus 1, here's my remainder. Notice that so far I've tried 4 different things and none of them were, I didn't find any factors, or consequently I didn't find any roots because I didn't get a 0 remainder any of those times. But look how much space it took up. And it was 3 lines per problem. So the chart is going to consolidate this work for you and give you 1 line per problem. So here's what we do. We start with giving ourselves room above and below, and we make a 0 row. The 0 row represents what we would get if we divided by x minus 0. So you see that I did that already over to the side. And I had 3, -2, 1, -4, and 6. Notice that those are actually the coefficients of the original problem. 3, -2, 1, -4, and 6. But after you've divided, those numbers represent what you have left, and 6 represents the remainder. So I'm going to make a remainder column. So this is how we set up our chart. Make the 0 row using the numbers from your problem, but the last number is in the remainder column. Do something to highlight the 0 row. You see I drew lines around it. You could use a highlighter, something like that, because every time you make a new row, you're going to use the numbers from the 0 row, because the 0 row represents this top row that you write every single time you do synthetic division. It's just the numbers from the problem. Okay, now I'm going to test x minus 1 by putting 1 in the box. Bring up the 3. Just like when you do synthetic division, you bring down the 3, bring up the 3. Now, here's where you do some of the synthetic division steps in your head. So we were writing down a middle row. That middle row we're going to kind of do in our head. So here's what we do. 3 times the number in the box, add the next number in the 0 row. So that's 3 times 1 plus -2, that's 1. 1 times the number in the box, add the next number in the 0 row. So 1 times 1 plus 1 is 2. 2 times the number in the box, add the next number in the 0 row. 2 times 1 plus -4 is -2. -2 times the number in the box plus the next number in the 0 row. -2 times 1 plus 6 is 4. You see we get all the same numbers that we got down here, but it's just taking up less space. Let's go again. Let's do 2. So this would be if we were checking to see if x minus 2 was a factor, or if we were checking to see if 2 was a root. Bring up the 3. 3 times 2, add the next number in the 0 row. 4 times 2, add the next number in the 0 row. 9 times 2, add the next number in the 0 row. 14 times 2, add the next number in the 0 row. 34, just like we got over here, 34. Okay, if I want to do 3, bring up the 3. 3 times 3, add the next number in the 0 row. 7 times 3, 21, add the next number in the 0 row, 22. I'm not saying you have to do all this in your head. You should grab a calculator whenever it becomes obvious that you might be making a mistake. 22 times 3, 66, plus the next number in the 0 row, 62. 62 times 3 is 186, plus the next number in the 0 row is 192. Now if you want to do negatives, you can just do them down here. Bring down the 3. 3 times -1 plus the next number in the 0 row. -5 times -1 plus the next number in the 0 row. 6 times -1 plus the next number in the 0 row. -10 times -1 plus the next number in the 0 row. And so on and so forth. Now, I would always go in order. Notice I went 1, 2, 3. I wouldn't skip around. -1. The next one I would do is -2, -3. And that's because we haven't gotten there yet, but we are going to need to look for patterns in these numbers. And if we don't have them in order, we won't be able to see the patterns. So again, you're just going to have to trust me that this chart is going to help you in many ways. Not only does it save you space with synthetic division, but it's going to help you in other ways. So let's finish number 5. Let's make a chart for this problem. So we're going to leave some space and make a 0 row. And the numbers need to be the coefficients from the problem. So we had 6x cubed, 5x squared, -17x, and -6. Okay, let's start with 1. Bring up the 6. 6 times 1 plus the next number in the 0 row, 11. 11 times 1 plus the next number in the 0 row, -6. -6 times 1 plus the next number in the 0 row, -12. Let's try 2. Bring up the 6. 6 times 2, 12. Plus 5, 17. 17 times 2 is 34. Minus 17 is 17. 17 times 2 is 34. Minus 6 is 28. Let's do 3. Bring up the 6. Getting my calculator ready. 6 times 3 is 18. Plus 5 is 23. 23 times 3 is 69, minus 17 is 52. 52 times 3 minus 6 is 150. Then I'm going to go down and try some negatives. Okay, I had to actually take a break there and pause and go teach a class and come back, so I hope that this transition isn't too awkward. Where did I leave off? Let's go ahead and do a negative. So let's try -1. So we bring down the 6 and then multiply by the number in the box and add the next number in the 0 row. So now we have -1. -1 times the number in the box plus the next number in the 0 row, and now we have -16. -16 times the number in the box is +16 plus the next number in the 0 row is +10. And remember, you can highlight that 0 row if just having lines around it is not enough to make it stand out. Always going back to that 0 row. -2, bring down the 6, multiply by the number in the box, we get -12 plus 5, and we get -7. -7 times -2 is 14, plus -17 is -3. Oh, good. It's looking like we got a winner here coming up, guys. -3 times -2 is 6, plus the next number in the 0 row is going to give us 0. So we have a root, finally. We have one root. It's x equals -2. And keep in mind that the numbers in here would be the numbers that you would have at the bottom of your synthetic division. So that represents 6x squared minus 7x minus 3. And if you set that equal to 0, it might factor, it might not. You might have to use the quadratic formula and find your roots. They might be irrational or they might be non-real. I'm just going to see what I can do here with 2x and 3x and 3 and 1. Nope, that's not it. Let's see here. What if it's 3 here, 1 here, minus plus? That works. Okay, so we end up with x equals 3/2, and we end up with x equals -1/3. And just a reminder, when we made our APRR list, way up there, we have 3/2, that's in the list. We have -1/3, that's in the list. Every rational root you get, -2, that's in the list, should be a number that was in your APRR list. So finishing it off, x equals -2, x equals 3/2, x equals -1/3. Okay. So here is the assignment for today. Thanks, everybody.